Sorry about that little interruption. My sitting outside because there's nowhere else in my house to go at the minute with my kids and my wife all over everything, and my dog started barking. So anyway, there he goes again. So basically, this is just a fancy way of saying that we have functions that are just shifted versions of the other functions. So that, and you will have noticed this, like cosine and sine, they're the same shape when you look at the graph. They both have that same wave shape to them. And what we can do is actually just shift by 90 degrees and actually find the other one. And you can do the same thing with tangent and cotangent. They're just shifted and mirror images of each other. So basically, we just have all these shiftings that we can do. So if theta is measured in radians, then you essentially have these same relationships by replacing the 90 degrees with pi over 2, because pi over 2 is the same thing as 90 degrees. So just replace them and you've got that. So how is this useful? Well, let's say that you already know that the cosecant of 21 degrees was about 2.7904, and you're asked to find the secant of 69 degrees. Well, we can use these relationships by saying, well, the cosecant of 21 degrees is equal to the secant, right, is equal to the secant of 90 degrees minus that 21 degrees. What was there? That's this relationship right here. And that gives us that we have the secant of 90 minus 21 is 69 degrees, which is what we're looking for, which means it is about equal to the same 2.7904. And we have that answer right there. Okay? So let's try another example here. Solving a right triangle. To solve a triangle means to find all unknown lengths and sides and angle measures, everything that's missing, given just a few details that make it fully solvable. So the measure of one angle of a right triangle is 90 degrees. The Pythagorean theorem allows us to find the remaining sides. So if you have two of the three sides, you can use a squared plus b squared equals c squared to find the missing one. And then once we have that, we can say that any two acute angles of the right triangle, that is going to be the two non-right triangle angles, are complementary. Because if you think about it, the total angle in any triangle is 180 degrees. This right angle is already taking care of 90 degrees of it, which means there's 90 left over for the other two to add up to. So that means they have to be complementary, which basically means angle A plus angle B is always going to equal 90 degrees. And then the third angle being 90 degrees gives us that total of 180. So let's take a look here and solve right triangle ABC if A is 45 degrees and side A is 5. So if we get that, we have a nice right triangle here. And we can say then that this is the 90 degree angle. That's what we're going to call C. We'll call this angle A, this B. That makes this A, this B, and this C. Now we know here that A is 45 degrees. So we'll go ahead and label that 45 degrees. Well, then we know that side A is 5, so we can put that in. So those two are given to us, and I'll do everything else in green from now on so you don't confuse it. Well, first thing we can say is that those two angles A and B are complementary, so that means they have to add up to 90 from that right there, and so that makes this angle up here also 45 degrees. That wasn't written very well. 45 degrees. And so now we've got all three angles. So now it's just a matter of finding the sides. Well, we know that if here we look at this, we can say that the sine of A equals A over C, which is going to give us the sine of 45 degrees equals 5 over C. Okay? And so then that allows us to find side C. C is equal to 5 divided by the sine of 45 degrees. And at this point, we should know the sine of 45 degrees is square root of 2 over 2. So this is 5 divided by square root of 2 over 2, which makes this simply 5 times 2 over the square root of 2, which is 10 over root 2, which is 10 root 2 over 2, which is 5 times the square root of 2. So just doing some algebra there. So that means we know now that C is 5 square root of 2. All right, now you don't always have to do it in this exact same order that I'm doing it, but you know, it kind of helps. So now we have 2 of the 3 sides, which means we can use Pythagorean theorem to get the other one. You also could note that in this case, well, I'll tell you about it at the end. Hold on a second. So we can then use Pythagorean theorem. We can say that a squared plus b squared equals c squared, and we know a and we know c. A is 5 and c is 5 root 2. And so what this does for us is it tells us that here we've got 5 root 2. We can actually rewrite that. If you're not good with these, it's sometimes a little helpful to make this square root of 25 times 2, which is the square root of 50, and it's being squared. Okay, so this side will just give us 50. The other thing you could have done is just square, and it would have been 25 times 2, because this would have been 5 squared would have been 25, and then square root of 2 squared would have been 2. It would have been 2. But either way you want to think about it. And so then this will be 25 plus b squared, and then that's going to end up giving us b squared minus equals 50 minus 25, which is b squared equals 25, which is b equals 5. So we now know that b is 5, and we have fully solved this triangle. Now, you may have noticed that these two angles are the same, and when these two angles are the same, they're going to both be 45, and that's also going to mean that these two sides are going to be the same as well. Okay? So if you had noticed that early on, you could have immediately said, well, b is 5, and then we could have just used Pythagorean theorem to find c, and not had to use the sine and cosines, but that's only in the special cases where those two angles are the same. Had it been something different, then you wouldn't have been able to just make them the same. So just pointing that out, that you don't think that's always going to be the case. Here we've got a 21-foot ladder is resting against a wall of a building. It's in such a way that the top of the ladder is 15 feet above the ground. So here we've got our building, let's say. Here's the ground, and we've got, that wasn't a very good ground. Here's the ground, and we've got a ladder resting up against it, and it's telling us that this side over here is 15 feet, and then it asks us how far is the foot of the ladder from the base of the building. It also tells us, oops, forgot this part, it's a 21-foot ladder, so this is 21 feet. And you'll notice if we take the ladder as the hypotenuse, we take this part of the building as one of the legs, and then this part of the ground is the other leg. We have a nice right triangle there. And if that's our right triangle, that makes this A, this angle B, this angle C. So this side is A, this side is B, this side is C. And we're back to just solving a right triangle based off the given information. So now we can go through and we can find that missing side, and we want to figure out basically how far is the foot of the ladder from the base of the building. So that means we need to find A. So find A. And we'll do that with Pythagorean theorem. A squared plus b squared equals c squared. And so we've got b, so we have a squared plus 21 feet squared. I didn't even write my feet. Not 21, 15. Sorry, 15 feet squared equals c, which is 21 feet squared. And then if you go through and do this, you'll get b equals 21 squared is 441 feet squared. And then the 15 feet squared is 225 feet squared. and then we have to take the square root of the whole thing because we have b squared. So this is about the square root of 216 feet squared. And then when you take the square root of 216, you get about 14, maybe ish. We're about 14, and the square root of feet squared is feet, so we're at about 14 feet. So this side over here, this A, is going to be about 14 feet. You could do it exactly in a calculator if you really wanted to see. And then after that, it's also solved the triangle. Well, that means we need to find the angles. So we have all the sides, so we can just start making relationships like sine of A, that angle there, if we want to find that, is going to be the opposite side over the hypotenuse. So that's going to be the 15 feet over the 21 feet, and the feet will cancel. And you're left with sine of 15 over 21, which means A is equal to the arc sine. We can use our inverse relationship of 15 over 21, and that's going to give us about 45.6 degrees. And so now we've got A, and now we need to find, well, angle C. Angle C is pretty easy. We know that's 90 degrees. We already even said that. So we've got the 90 degrees there. And then the last thing you have to do is find the other angle. Now we know that it's complementary, so you could do A plus B equals 90 degrees, and then you'll get A 45.6 degrees plus B equals 90 degrees, which tells us that B is about 44.4 degrees. You wouldn't want to round until the end if you were doing this in your calculator. If you don't like doing that, you could also do things like sine of B is whatever that A side was, 14-ish feet, whatever it was, over 21 feet. You'd need that 14 number exactly from a calculator, and then take the arc sine. And so B equals the arc sine of the 14-ish number over 21. Or you could have done the cosine of B, which would have been, by the way, I'm looking at this. Sorry, I didn't point this out. Sine of B would be the opposite side from B, which is that 14, over the hypotenuse. And then the cosine of B would be the adjacent side, the 15 feet, which we know exactly, over the hypotenuse, which would be the 21 feet. You could even do something with the tangent if you wanted, but since we know 15 feet without it being a decimal, this using cosine is probably better than using the sine, and we get that B is going to equal the arc cosine of 15 over 21. Those feet cancel. And that would probably give you your most exact answer, and ultimately you're going to get about that for B. Okay? Some other applications of this, you can use this to find angles of elevations and angles of depression. This kind of stuff is used to find distances. It's called triangulation, where say you have a canyon that you're looking across and you can't cross it, and there's a tree here, you know, some tree like that. And if you're here and you need to know how far across it is, across the river or canyon or whatever, you can stand right here and you can then take and walk a certain distance this way. Some distance, we'll call that side A. And then you could then use two sticks and actually line one up pointed at the tree, line one pointed up right where you first started, and find this angle here, this angle theta. And then you could draw this here if you were straight across from the tree when you started, and you have that as a 90-degree angle. And then you could solve the triangle like we did above. That's called triangulation. They talk about triangulating people's locations in movies and stuff all the time using cell phones. That's actually the wrong term. What they mean to be saying is they're using trilateralation, which is the overlapping of circles and spheres to find a unique point, kind of like what they do for finding the epicenter of earthquakes. This is the actual triangulation method, and it uses a triangle, but it's kind of gotten used wrong so many times in movies. I think they just keep doing it whether they know that's right or not. It is actually two different things. So anyway, That's just about it.